again, we're looking at applications of trees, and we looked at the first two, the binary search trees and evaluating mathematical expressions using expression trees. If you notice, all of these applications are applications of binary trees. There are other applications of trees in general, but these are the ones that I've chosen, and they all happen to be binary trees. The third application we're going to look at is the problem of encoding characters, meaning letters, numbers, and so on in our alphabet, in binary. There are many different encodings. One of the ones we're going to look at is called Huffman coding. And we'll talk about the problem in a second, but Huffman coding is a piece that's used in a lot of familiar compression algorithms. If you've used JPEGs for images or MP3s for audio files, these compression algorithms include Huffman coding as part of them in one of the steps in compressing or encoding data like that. So it's a very common tool that's used in a variety of places that you're familiar with. So we'll look at Huffman coding. So the problem is we have, for our example, we're going to use the English alphabet. So we have 26 letters in the English alphabet. We're not going to worry about numbers or other characters. We're not going to worry about things like commas and periods and exclamation points and all that. We're not going to worry about any of those. For right now, we're just going to worry about the 26 letters in the English alphabet. So we can use bit strings to encode or represent letters. The question is, how do we do this? Again, there are a variety of ways of doing this, and this example we're looking at is where we want to encode it as efficiently as possible. Most encodings, like if you think about like Unicode or ASCII or something like that, they are not as concerned with efficiency. They just want a regular pattern that's easy to follow. We're looking at how do we do this as efficiently as possible. The history behind Huffman coding is a little bit interesting. If you want to look that up, you can and read about how it was developed. But the idea, again, is we want bit strings to represent letters. So if we need 26 possibilities for the 26 letters, how many bits do we need? So our first solution, and this isn't the one we'll land on, but the first solution is if we need 26 different possibilities, having 2 bits wouldn't be enough, right? We know from our counting methods that that would only give us 4 possibilities. 3 would give us 8 possibilities, then 16, and then 32. So it would require 5 bits to get enough different variations that we could cover all 26 letters. So we would need bit strings of length 5. So just over 1 byte for each letter, right? Because 2 to the 5th is 32, which is greater than 26. So that's what we need to cover this. And that's fine. Having just over 1 byte for each letter is not terrible. Certainly better than some of the encoding algorithm or encodings that are out there. But the question is, if we're really concerned with efficiency, if we're trying to compress something, can we do better? And the answer, of course, is yes. If you think about this, some of the letters in the English alphabet are going to be used more commonly than others. So for instance, E, N, T, S, right? These are the most common letters in the English alphabet that are used in English, at least. If you were writing in a different language, you would have different frequencies. Different letters would be more common. But for this process to work, we're going to have that information about how common each letter is, how often each one is used. So if we know that, the genius of Huffman coding says, let's use shorter strings for the more common letters, and then use longer strings for the less common ones. And the idea is that on average, we'll end up using fewer bits because the letters that we use most often we'll be able to use as efficiently as possible. So let's say, for example, we had something like this. Let's say we represented E with just a single bit 0. And we represented A with a single bit 1. And then we represented T with 0, 1. And I'll stop there because it's enough to illustrate. I don't know if you've spotted it, but there's a problem with this. The problem is, suppose I had a string like 0, 1, 0, 1. What would that read as? And if you think about it for a minute, you should be able to see the problem here. The problem is that this string could be read a number of different ways. You could read it as the first 0 being E, and then the 1 being A, and the 0, 1 being T. Or you could read this first 0, 1 as T, and then the 0 as E and the 1 as A. Or you could read both 0, 1s as T, or you could read all the zeros as E and all the 1s as A. Right? So there's a variety of ways we can read that, which is not good. Right? We want to have a consistent way of writing this down because otherwise there's no way of knowing after we've encoded it what we started with. There's no way to get back to that. So Huffman coding says there's got to be a better way to create this scheme so that we don't have any ambiguity to the message. And that's the key. So the key to Huffman coding is something called a prefix code. And if you notice, the problem we ran into here was that when you hit a 0, it could either be E or it could be the beginning of T. And if the next bit was a 1, then that could be a T. So the idea of a prefix code is one that avoids having any value for one character being the beginning of another one. That's the idea. If the prefix code can avoid having one encoding being the beginning of another one, then we'll avoid the problem we just ran into. So that's the idea. The code for one letter cannot be the beginning of the code for another letter. So let me give you an example of a prefix code. If I had 0 for E, and then 1, 0 for A, 1, 1, 0 for T, 1, 1, 1, 0 for N, 1, 1, 1, 1 for S. If you look carefully, there's no question, there's no ambiguity, because none of these is the beginning of any others. So a 0 isn't the beginning of any of the others. None of the others begin 1, 0. None of the others begin 1, 1, 0, and so on. So this is an example of one simple prefix code. And there's a way to write this, or a way to draw this using a binary tree. What you can do is you can start at the beginning of a string, and if there's a 0, you go to the left, and if there's a 1, you go to the right. So going to the left once and getting a single 0, that's where you find E. If you go to the right once and you write down a single 1, you haven't found any of these. None of them are just a single 1. But if you go from there and go to the left or go to the right, so going to the left, the encoding would look like from the beginning 1, 0. So the one that looks like 1, 0 is A, and 1, 1 is nothing. Nothing, no letter is there, but we can keep going from there. Here's the A, and then if we keep going, we do another 0 and 1. The 1, 1, 0, that's T. The 1, 1, 1 is nothing. So that would split again. And at the end of that, the 1, 1, 1, 0 would be N, and the 1, 1, 1, 1 would be S. So this tree, this binary tree, describes a prefix code. And if you think about why a binary tree represents a prefix code, because each branch only can have 2 children, if you keep going down this, each letter is at the end of one of the final branches. And the binary part is important because we're working with bit strings, so we have two possibilities, ones and zeros. So since every letter is at the end of a trail, there's nothing that lies past it. None of them can be the beginning of another. So you can't have 1, 0, anything because there's nothing after the A. So none of them fit into that category. So a prefix code can be represented with a binary tree, and we can use a binary tree to create a prefix code. Now let's say, for example, given this code, we wanted to excuse me, decode 11111 0 11100. To do this, we would start going through until we find a letter. So when we read a 1, none of them is just 1. None of them is 2 or 3 ones. But when we hit 4 ones in a row, that has to be S. And then starting after that, when we read a 1, that's nothing yet. But 1, 0 gives us an A, and that's the only possibility. Nothing else continues on from 1, 0. And then continuing on, the 1, 1, 1 gives us nothing, but 1, 1, 1, 0 gives us N, and then the final 0 is E. So it's the word sane. So that's an example of a prefix code that's been created for us. But Huffman coding is the process that we're going to use to generate these codes, to generate prefix codes that take into account the frequency of letters and gives shorter strings to more frequent letters, which is basically what happened here. The more common letters ended up with a shorter string, which is good for efficiency's sake. All right, so Huffman coding, the goal is to build this efficient prefix code using the frequencies of letters. So we have to be given a list of characters, and we have to be given their relative frequencies. So relative frequencies means if you add these up, you're going to get 1. Hopefully, if I've done everything right. And so these are like percentages, these relative frequencies. So in this example, we're only working with 6 letters, and we're assuming these are the only 6 letters we have to work with. Working with 26 is no different, it's just more tedious. So we're going to stick to examples that we can do relatively quickly. So we have the relative frequencies. Notice that in our made-up example, F is the most common letter, and then E, and then D, and so on. So there's kind of this order to them. Now, here's how Huffman coding works in short. You start by listing in this order from least to greatest frequency. Now this one's already done for us, so we're going to keep this same ordering. But if it weren't, we would write them in that order to begin with. And then at each step, and you'll see this in the example we'll do in a second, you're going to combine the 2 smallest remaining, the 2 with the lowest frequencies that remain. You're going to combine those 2 together, and then you're going to reorder, thinking of those 2 as one unit. Now, this will make more sense with an example, but when we combine these, what we're going to do is take something like this and create a little piece of a binary tree where we make each end of that one of the 2 characters we're combining. So when I say combine, that's what I mean, is create a little segment of the binary tree. And when we do this, just for convention, we're going to make the higher frequency one the 0 and the lower frequency the 1. You could do it the other way around. We just need to pick one ordering to do it. And that's the one we'll do just to be consistent. Okay, so let's see this in action. Makes a lot more sense than talking about it. So I'm going to order these in order. So I have A, B, C, D, E, and F. And we're basically going to string together a tree with these. It's like putting ornaments on a Christmas tree or something. I'm going to list their frequencies so we have them to compare to. Okay, So at each step, we're going to combine the two lowest frequency ones. So that would be these two right here, the A and the B. We're going to combine those and make a little piece of a tree like this. Remember, the higher frequency one is going to go on the left side with the 0. So it's going to look like that, and like that, with a 0 here and a 1 here. Now when we do that, that combined piece has a frequency of 0.18, the sum of them. So if we're reordering, that's going to go after these two, but before these two. So we're going to have C and D over here, and E and F still over here. So we're slowly constructing a binary tree by building one segment of it at a time. All right, so the next stage we select the two lowest frequency ones. Again, these are the C and the D at the bottom. Now when we combine these, that's going to have a total frequency of 0.27, which is going to put it right here in our newly ordered list. So now at the bottom of the list is going to be the BA segment. Then there's going to be an E, then the DC segment. Again, the higher frequency one goes on the left, so the D and then the C on the right, and then finally F. So the AB has a 0.18 frequency, then 0.2, then 0.27, again that's the sum of these two, and then 0.35 at the end. So now the two lowest frequencies are this one, this E plus the segment AB. Now when we combine those, that's going to have a frequency of 0.38, so that's going to be the very last thing in the list. But let me show it first, just to show you how it works. So over here at the end of the list, we're going to have a piece here. The higher frequency piece of these two, which is the E, is going to go on the left. So E is going to go over here. And then on the right side, I'm going to pin this tree right there. So we're going to have the B and the A like this. So that is how you construct this tree out of these two. Is you combine it by putting one piece on the higher frequency piece on the left, and then just copy and paste this on the right-hand side. All right, and then we have the DC piece left here, and the F left in the middle. Now with the frequencies again here for reference. So this last one's going to have a frequency of 0.38. Now we're going to combine these two, and then we'll have one more step. So again, when we combine those, the total frequency is going to be 0.62, so that's going to be over on the right here. The F is higher frequency, so it goes on the left, and then on the right side, we copy and paste this little segment of the tree. And then over here, I'm going to copy what we had before. So this one has a frequency of 0.38 and 0.62. Which means we only have one more step to do, which is to combine both of these in the one final tree. This piece is the higher frequency, so it's going to go on the left. So on the left here, I'm just going to copy and paste that. So we have F over here, and then we have DC over here. Then on the right side, I'm going to copy and paste this. So we have E over here, and then we have B and A like this. So that's the total final tree that we've created. And at each stage, these left-hand turns are zeros, and the right-hand turns are ones. So if you want to know the code for any given letter, you can just trace down the tree until you get to it. So A, for instance, would have a code of 1, 1, 1. B would have a code of 1, 1, 0. E would have a code of 1, 0. F would have a code of 0, 0, and so on. So we can go through and fill all those out. So A is 1, 1, 1. B is 1, 1, 0. C is 0, 1, 1, D is 0, 1, 0, E is 1, 0, and F is 0, 0. So again, notice that these two most frequent letters have the shortest codes, and they only require 2 bits to write them down, and then the higher frequency ones require 3 bits. So on average, we're going to end up under 3 bits per letter. Because since we have 6 of them, if we just did it as a more straightforward one, we would need 3 bits for all of them to get 8 possibilities. But as it stands, we're going to have a slightly better average cost to sending a message. So the question is, how good is this? We can check the average number of bits to send any given character. So the first 4 characters require 3 bits, the last 2 require 2, and I'll write down their frequencies again for reference. And so to find the average of this is a weighted average, where we're going to multiply the length by the frequency each time, and then add together the results. So a weighted average just works like this, where you multiply your values by the weights in each case. So the average will be 3 times 0.08 plus 3 times 0.1, and so on. So I'm taking each cost times the frequency of that letter. And if you add these all up, you should get 2.45, which again is significantly lower than 3. So if you're sending a long message, you would see large savings from encoding it this way. So Huffman coding saves you by giving you a more efficient way of encoding. So you'll have homework examples to practice this, to go through and use Huffman coding to encode a set of letters. And you can follow this example to see how that works. I do want to show you one more example to illustrate something kind of unusual. We can take a smaller example where we just have 3 letters, and without going through it, I'll show you what the final tree looks like. If you want to pause this and try doing the example on your own and see if you can get to this tree, that would be a good idea. But the tree that you should get at the end looks like this. We have A here, and then B and C. And again, notice that since A has a much higher frequency than anything else, it gets 1 bit, and then the others take 2 bits. So A would be represented as 0, B would be 1, 0, and C would be 1, 1. So if you do this, the average number of bits to encode a character in this would be the number of bits times the frequency again. So A would have 1 times 0.8, B takes 2 bits times its frequency, and C takes 2 bits times its frequency. And if you add this up, you get 1.2, which is pretty good, just over 1 bit per character. That's not bad. But there's something you can do to make this a little bit better. If you take pairs of characters, so since there are 3 characters to begin with, A, B, and C, there's going to be 8 possibilities for pairs of them, right? So we have A, B, A, C, and so on, all these possibilities. Now, if you look carefully, if the probability or the frequency of an A is 0.8, the frequency of AA should be 0.64. So each of these frequencies that I have listed here are just the product of the 2 frequencies of the 2 letters we've chosen. So this would be the product of the probability of A and the probability of B. So 0.8 times 0.19, and so on. So you can fill that out, and I won't take the time to go through the rest of them, but it's the same idea. Now if you do this, again, if you want to take this and use it for practice to build the prefix code, that would be a good idea to pause the video and try that yourself. But I'll just show you the answer that you should get. Will look something like this. So we have Over here we have AA. Over here we have AB at 1, 1. And then continuing on, this is a long one, but if we keep going, we get something like this. All right. So there's our tree, which means that AA would be encoded with a 0. AB would be encoded with 1, 1. AC would be encoded with 1, 0, 1, 1, 1. Notice how low the frequency is, so it has a higher bit count, a longer length. BA would be 1, 0, 0. BB would be 1, 0, 1, 0. BC would be 1, 0, 1, 1, 0, 1, 1. Again, an even lower frequency, so it has a longer string. Then CA would be 1, 0, 1, 1, 0, 0. CB, and so on. Okay, so there's the final code. And what's significant is not how we do that, but it turns out that if you calculate the average here, you get 1.66. And I'll leave that to you to practice to see if you can get that value. But an average of 1.66 means that this is slightly more efficient, because if you think back, when we encoded one letter at a time, any 2-letter combination would take an average of 2.4 bits to encode. This one we can do with 1.66. So there are times where if you take a string of letters like this, if the frequencies are really lopsided like this one is, there are times where lumping letters together and making combinations of them can make your encoding slightly more efficient. Now, that doesn't always work, and sometimes you just get more, you're doing more work for no gains. And there are times where you can go on to 3-letter combinations and so on. And it gets slightly more advanced to figure out how far to go in this process, but you could do it by trial and error. But I just want to show you that example as one interesting thing that can happen sometimes when you're doing this, that combining characters together can possibly give you efficiency gains.